the x-axis at both of those zeros. There we go, that's better. All right, make sure you know how to use the rational zero theorem to list all possible rational zeros. So let me go through this problem for you. And I need a pen. So it basically goes like this. You have to find the constants P and Q. Okay, so here's our function. F of x equals x cubed minus 17x squared plus 3x minus 10. And this is how you identify P and Q. P is the constant term. So here it's negative 10. And Q is the leading coefficient. So it's the coefficient on the term that has the highest power on x. So here 3, 2, 1, 0, this is the highest power. This is the leading coefficient. If it's not there, it's understood to be 1. Okay? You want to find all possible ratios of P to Q. So what are the possibilities of all the factors? So P, you list all the factors of Q. So I'm going to write that here. List all factors of P. And then you're going to divide that by a list all factors of Q. So it's the factors of the constant term divided by the factors of the leading coefficient. So in this case, and that includes positive and negative. So what are the factors of 10? Well, the factors of 10 are, always include 1, plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. Okay, so 2 times 5 is 10, and 1 times 10 is 10. So those are all the factors. Now, the factors of Q, well, Q equals 1, so it's just plus or minus 1. Okay, because negative 1 times negative 1 is 1, and 1 times 1 is 1. Okay, now what are the possible ratios? Well, you could have 1 divided by 1. Okay, so that's plus or minus 1. 2 divided by 1, that's plus or minus 2. 5 divided by 1, that's plus or minus 5. And then 10 divided by 1, plus or minus 10. So these are the possible rational zeros. These are possible. That's the key word. Doesn't mean those are the zeros. It just means those are the possibilities from the rational zero test. Okay, that's how you do the rational zero test. So if I say list all the possible rational zeros, then this is what you would do. You would take your constant and your leading coefficient, form a ratio, and then list all the possible factors in the numerator and in the denominator, and then do your division like that to get your answer here. Okay. So C is the correct choice. All right, let's look at one more example like this. I think we have just one more. We have this time f of x equals 6x to the 5th plus 4x to the 4th minus 10x squared plus 13x minus 2. Okay, so P, we're looking here at this constant term. The factors of 2 are plus or minus 1, plus or minus 2. And then the leading coefficient is 6. So we have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. These are the factors of possible factors of 6. And then to find all the possible rational zeros, you take 1 over 1, 1 over 2, 1 over 3, 1 over 6. So 1, 1/2, 1/3, 1/6, and those are, of course, plus or minus for all of them. And then you go 2 over 1, that's 2, plus or minus. 2 over 2, that's 1, but we already have that in our list. 2 over 3, that's 2/3. And then 2 over 6 is 1/3, but we already have that in our list. So these are the possible rational zeros right here. So C is the correct answer. The following function is given. Now it says list all rational zeros that are possible according to the rational zero theorem. So the last two are multiple choice, but of course the test that you're taking is going to not be multiple choice. So, but I think this has multiple parts to it, looks like. So there's a point to all of this. The first step is to list the possible rational zeros. Okay. So P over Q, the factors of 12 are 1, 2, 3, 4, 6, 12. And the factors of, these are all plus or minus. And the factors of the leading coefficient are 1, so it's just plus or minus 1. So dividing by 1 is not going to change any of these. So these are the possible rational zeros. The next part says, use synthetic division to test several possible rational zeros in order to identify one actual zero. Okay, so I'll just start and work through my list. Let me show you how we do this by synthetic division. The thing you need to know about synthetic division, when you take a value and you perform a synthetic division on it, what you're doing is you're checking to see if it's a zero or not. And if your remainder in your division is 0, then you know that the value that you were testing is actually a 0 for your polynomial. Okay, so this is how it works. This is my polynomial here. I write down the coefficients of my polynomial in order. They have to be in order, and you have to put a 0 if there's a term missing, then you have to put in a 0. But We have an x cubed, we have x squared, x, and a 0 term, so we're good. We don't have to put any zeros in there to hold. 0 kind of holds a place of a term. Then we're just going to pick from this list. Since there are finite many, we can just start down the list. 1, 2, 3, 4, 5, 4, 6, 12, and then the negatives. So I'll start with 1. Bring down the 1. 1 times 1 is 1. Then add these two numbers, I get -2. 1 times -2, that's -2. Add these two numbers, that gives me -6. 1 times -6 is -6, and add that to 12 gives me 6. What this tells me is that f of 1 equals 6, okay? And in order for 1 to be a 0, this has to be 0, and it's not. It has a remainder of 6, and therefore the factor x minus 1 does not divide evenly. In other words, x minus 1 is not a factor of f of x. If it were a factor, then this would have been 0. Okay, so but that's okay. We try our next choice in the list. This time it's 2. So I'm going to do the same division with the same coefficients, except instead of plugging in a 1, I'm going to plug in 2. Bring down the 1. 1 times 2 is 2. Add to -3, that gives me -1. -1 times 2 is -2. Added to -4 is -6. 2 times -6 is -12. Added to 12 is 0. Aha, we got a remainder of 0. What this means is that not only is f of x has a factor of x minus 2, it also tells us that in order to, if we factor that, these coefficients are the ones remaining. Those are the coefficients of the dividend. I'm sorry, the quotient. Okay, the quotient is the polynomial on top when you do your long division. So this becomes, now since this is a cubic polynomial, when you divide by a factor with degree 1, then this is going to be degree 2 because you reduce it by 1, the degree. You reduce the degree by 1. So this is going to be x squared times -1x, that's minus x, minus 6. So you just put the coefficients there. And this is how we factor, okay? And then to continue now the factorization, we can go ahead and factor this, right? Which is just x minus 2. This becomes x minus 3 times x plus 2, right? If you FOIL that, you can see -3x plus 2x gives me -x, and 2 times -3 is -6. So what I've done here is by finding one of the factors, I'm able to factor the remaining polynomial there. And so the zeros, are 2, 3, and -2. Because you set each factor equal to 0 and solve it, and you get these as solutions, okay? So let's go back to our problem. One rational 0 of the given function. Let's see, the first one I found was a 2. Then it says use the 0 from part B to find all the zeros of a polynomial. And I found 2, 3, and -2. And okay, that's how you do it. So the next one, I'll do this again. I'll show you how this works. f of x equals x cubed plus 7x squared minus 71x minus 77. Okay, the first step is to list the rational zeros. So P over Q, the factors of 77 are plus or minus 1, plus or minus 7, plus or minus 11, and plus or minus 77. And then the Q, the factors of the leading coefficient are plus or minus 1. So these are the possible rational zeros. Now it says use synthetic division to test several possible rational zeros in order to identify one actual zero. And looking at this, I would say that it looks like just by looking at it, thinks -7 is one of the rational zeros. So just to save time, I'm going to start with -7. And I have the coefficients here, 1, 7, -71, and -77. So I bring down the 1, multiply by -7, and that's 0. -7 times 0 is 0. And that's -71. And then we have, but I was wrong there. I was wrong about the -7. So I was just guessing, but turns out that I'm not going to get that. So I'm going to try, let me try 1. I hope I copied this correctly. Let me just double check. X cubed plus 7x squared minus 71x. Yes, I did. Okay, good. So bring down the 1. 1 times 1 is 1. Then we get 8. 1 times 8. And I'm adding, so that's going to give me -63. And that's not going to work. So let me try -1. Multiply by -1 gives me -1. Then I got -6. I'm sorry, +6 times -1 is -6. -77 times negative is 77. There's the one I'm looking for, okay? So my factor is x plus 1. So this means that x plus 1, because you always take the opposite sign of your 0 to get, so in order, if I plug in -1 here, I'm going to get 0. So the factor is x plus 1. And so f of x equals, that's a 6, by the way, x plus 1 multiplied by, now we go to these coefficients right here. This is the x squared term, plus 6x, you just work your way down the line, minus 77. And now we need to factor this, okay? And looking at it, I'm not sure that I can factor that because, let's see, The difference between 11 and 7 is 4, and I've got a 6 here. So you know what I'm going to have to do here? I'm going to have to use the quadratic formula to find the other zeros. Okay, so I want to solve x squared plus 6x minus 77. In order to find the zeros, this whole thing has to equal 0, right? Because x plus 1 times 0 is going to give me 0. So I set my quadratic function equal to 0, and then I get x equals minus 6 plus or minus the square root of 36 minus 4 times 1 times negative 77 all over 2 times 1. That's the quadratic formula. And 4 times 77, notice the double negative, that's going to be positive. 4 times 77, that's 280 plus 28. That's going to be 308. And then the 36. So altogether, that's 344. So we have x equals minus 6 plus or minus the square root of 344 over 2. And now I want to simplify this. Now I bet you they want decimal answers. Let me go check and see what they want exactly for answers. It says use a comma, type in integer or decimal, rounded to 3 decimal places as needed. So I'm going to do the decimal rounded to 3 places. So let me go ahead and use my calculator. For the test, you won't have to do the calculator. You can just leave it in simplified form when you using the I'm not picky about what form it's in, but because we're doing MyLab math, we need to have the exact answer. So let me just go ahead and do that calculation. So we have the quantity of negative 6 plus the square root of 344. And then that whole thing is divided by 2. So one of the answers is going to be 6.274. And if I go back and do a minus square root of 344, and then that whole thing divided by 2, we get negative 12.274. So we have negative 1, comma, 6.274, comma, negative 12.274. Okay, so like I said, what I really want you, I don't want you to worry about, getting the right calculation so far as your answers. I might take a point off or half a point if the answers are wrong. What I really want to see is that you understand what you're doing when you go through this process of using the rational zero test to check for a 0, then trying to factor or use the quadratic formula to find the other 2 zeros. That's the main point. Okay. Wait, the next question is basically the same thing that we've been doing. Let me come back to that one because I don't want to take too much time to do this. Let's see. Number 9 is the one we're coming back to. Okay, here it is. Answer the following questions about the equation below. List all rational roots. That's another word for zero, okay, that are possible according to the rational zero theorem. So the solution, so this is just another way of writing. Instead of looking for the zeros of a function, you're looking for the solutions of this equation. So we can see the factors of 12 are plus or minus 1, 2, 3, 4, 6, and 12. So D is your correct answer. And then basically the same thing that we did, use synthetic division. I think the reason why I have this one in here is because it's written in a different way. Instead of giving the function, it gives you an equation. But basically, you're doing the same thing. And I want to show you about the synthetic division on this one. I'm just going to write down this real quick because I want to make a point. We're missing a term in here, as you can see. Okay. So this is an equation about this function. So finding the solutions to this equation amount to finding the zeros of this function. And if I list the coefficients, I have 1 as my leading coefficient because this is the highest power on x. Then notice their x squared term is missing. So you've got to have that 0 in there when you're doing your synthetic division. Be careful about that. Then this term, the x term, is negative 34 and then negative 12. So you've got to have a coefficient for every term, even the missing ones, and you put a 0 where the term is missing. And if I pick, let me think. I'm going to try 3. Bring the 1 down, multiply by 3. No, that's not going to work. I think it's 12. 3 times 3 is, yeah, it's 12. It's 12 as a factor. Let's try 12. Well, let me finish this. You add these two together to get 3. 3 times 3 is 9. And then you subtract, so you get negative 25. No, yeah, 14 minus 9. And then you get 3 times negative 25 is negative 75. And you add these, so you get negative 87. What does this tell me? All this tells me is that f of 3 equals negative 87. In other words, f of x being this polynomial. So make sure you know how to evaluate a function using synthetic division. And this is all you do. You take your value that you're plugging in, the 3, and your remainder is the answer. Okay? But like I said, I think 12 is the correct 0. Let me try that. Bring down the 1, and you get 12. 12 times, that's not right. Oh, well, I don't want to take too much time doing this. I could sit there and go through that whole list. I thought 12 was going to work. Bring down the 1. 12. Yeah, then I get 144. I don't think that's going to work. Okay, let me go on because I've done already a couple examples like this. So I don't want to waste too much time on these. Like I said, don't worry about finishing this assignment for those of you who are Zooming. I'll just give you full credit for, doing a good faith attempt at it, and only the ones that I actually do for you. Okay, domain of a rational function. Here we go. That's on my list here, I'm pretty sure. Here we have h of x equals x plus 8 over x squared minus 64. Okay, this is a rational function. And so there's a section 3.5 and 3.5 of 3.6. We talked about rational functions. And let me see if I can get the focus in on that better. Not really. Okay. You need to be able to find vertical asymptotes, find the horizontal asymptote, find the location of a hole, find x and y intercepts. And I forgot to put find domain. Better add that to my list. I better update this and send out another email. Find out or find the domain of a rational function. Okay. Find the domain of a rational function. Don't forget that. I forgot it on. Here I had find the domain of a logarithmic function, but I forgot the rational function. Okay, there we go. So basically the domain is all real numbers. So here you can see the set of all x such that x is not equal to two numbers. Because I have a quadratic function, if I plug in an 8 here, 8 squared is 64. 64 minus 64 is 0. You can't divide by 0. So 8 has to be tossed out, as well as -8, because when you square -8, you also get 64. So, and then you subtract 64. So those are the two values that have to be thrown out. So when you're doing the domain of a rational function, you always say all real numbers except, and so the ones that cause the denominator equal to 0. Now, vertical asymptotes are basically the same thing. You set the denominator equal to 0, and then you solve. So in this case, x squared plus 2. Now notice x squared is positive, and you're adding 2 to that. So the denominator is always positive. It can never equal 0. So there are no vertical asymptotes, and as well, there are no holes. Okay? Oh, wait. There are no discontinuities right here at the bottom. I think I have 4 questions like this on the test, so make sure you know how to do these types. Check out the review. Okay, let's look at this one now. F of x equals x squared minus 81 over x minus 9. We're looking for holes and vertical asymptotes. So a hole occurs when your numerator and denominator share a factor. And we can see that's exactly what's happening right here. We have the numerator is x plus 9 times x minus 9. And then the denominator is x minus 9. So we don't have a vertical asymptote because these can cancel. And so this is kind of like, sort of like x plus 9. But the fact you're not really supposed to cancel it when you're considering the function itself and looking for holes, this just tells you that there's a hole there. Because even though it cancels out, you still have this x minus 9 in the denominator. And because this balances out that fact and it kind of makes it go away, there's still a hole when x equals 9. So whenever you have a factor in the numerator and denominator that match like that, this means there is a hole at x equal 9, okay? Because x minus 9 is equal to 0 implies that x equals 9. So this factor is in the denominator, so that produces a hole. Okay, so if you look back at this multiple choice, so out of 175 points, there are 4 problems like this on the test, and that amounts to 20 points because they're each worth 5 points. So make sure you don't want to lose those 20 points. Make sure you know how to do this. Okay, so it says here, there are no vertical asymptotes, but there is a hole corresponding to x equal 9. Okay, let's look at this one now. We have x minus 6 over x squared minus 36. Okay, so I'm going to factor the denominator now. And you can see I have a common factor. The numerator and denominator share a common factor. So this means there's a hole at x equals 6. Because if I plug in 6, I get 0. 0 divided by 0. Okay, that gives you a hole. But this one doesn't have a factor that goes with it, but it's still in the denominator. So this one right here means I have a vertical asymptote at x equals negative 6. Because if I plug in negative 6 here, I'm going to be dividing by 0. So it's undefined because that's in the denominator, but there's no factor that goes with it. So it's not a hole, it's a vertical asymptote. So if it's missing a factor in the numerator, it's a vertical asymptote. If it has a matching factor, then it's a hole. Okay? See how easy that is to do? So you don't want to miss out on those 5 points for each of those 4 problems, okay? Just saying, not that hard. So let me think here. See, there's a vertical asymptote at x equals negative 6. And then there's a hole corresponding to x equals 6. All right. So to find vertical asymptotes, you set the denominator equal to 0, looking for holes. And of course, a hole does not give you an asymptote. It gives you just a hole in your function. But here, what about horizontal asymptotes? Well, the way you do horizontal asymptotes is you look at the leading coefficient of the 2 polynomials, the numerator and the denominator. So we have, in this case, 18x over 9x squared plus 1. But before you look at the leading coefficient, you have to look at the degree. Okay, so if the degree of the denominator is greater than the degree of the numerator, okay, this is important. If the degree of the denominator is greater than the numerator, then y equals 0 is a horizontal asymptote. Okay, so that's exactly what we have here. We have the degree of the denominator is 2. The degree of the numerator is 1. So 2 is greater than 1, and so y equals 0 is a horizontal asymptote. Okay, now if the degree of the denominator is less than the degree of the numerator, there are no horizontal asymptotes. And if the degree of the numerator and denominator are equal, then you take the leading coefficients. Y equals P over Q, where is a horizontal asymptote, where P is the leading coefficient of the numerator and Q is the leading coefficient of the denominator. Okay. So possibly, let's see. I'll let you finish writing that. So there are three situations. If the degree of the denominator is greater than the numerator degree, then y equals 0 is a horizontal asymptote. If it's less than, then there is no horizontal asymptote. And if they're equal, the 2 degrees, I mean, then the leading coefficients determine the horizontal asymptote. So let me see if there's an example. So this one is y equals 0. Notice that now in this one, the degrees match. If they match, then you take the leading coefficient. So 14 divided by 7 equals 2. So y equals 2 is a horizontal asymptote. And that's all I had for that one. If it's the numerator, then there are no horizontal asymptotes if the numerator has greater degree. Okay, I'm looking at the clock here, and I just want you to I'm kind of short on time, but if I don't get through everything, what I'll do is I'll post this, this video will be in the cloud recordings, and I'm probably going to upload it tonight and then post it in my YouTube list. And then I teach the same class at 11 o'clock. So I will start where we leave off. And so that, you won't miss out on anything. You can go check out that video that I upload, okay? So after I'm done teaching today, I'll upload 2 videos to YouTube, one from this class and one from the other one. And that will be plenty of review for you if I don't get done, with everything today. Okay. Are there any questions so far? I know I'm zooming through this. Of course, it is a review, but if I'm going too fast or if you have any confusion, please stop me now because you won't be able to ask me during the test. So, okay, so now this brings us to section 3.6, where it says solve the polynomial inequality and graph the solution set on a real number line. And then it says express the solution set in interval notation. So here we have x minus 9 and x plus 5. And we're asking, when is that polynomial greater than 0? So the x-axis represents kind of a tipping point. On one side, the function is positive, and on the other side, it's negative. So when it crosses, or when it's when it's on the x-axis, excuse me, let me take a drink here. The function is 0 on the x-axis. So if I plug in a 9 here, that's one of the zeros, and -5 is the other 0. So if I plot these on the x-axis, I get -5 and 9. What it does is it divides up my x-axis into 3 intervals, and the function crosses from positive to negative or from negative to positive only at these 2 points. So on this entire interval, the function is either positive or negative. So all I have to do is pick one point like -6. And if I plug in -6, I get -15 times -1. That's 15. Is 15 greater than 0? True. So if I plug in -6, I get a true statement. If I plug in 0, so I'm going to pick 0 now because it's between -5 and 9. If I plug in 0, I get -9 times 5, -45 greater than 0. That's false. And if I plug in 10, okay, so I'm going to pick 10. 10 minus 9 is 1. 10 plus 5 is 15. 1 times 15. Is 15 greater than 0? That's true. So my statement is true and on these 2 intervals. So, and I don't want to include -5 and 9, because if I plug these in, either one of these, I get 0, and 0 is not greater than 0. So I have to exclude my values here. So -infinity to -5, along with 9 to infinity, those 2 intervals. So here's infinity, here's -infinity. From -infinity to -5, and then from 9 to infinity, that's true. The middle here, it's false. So I throw out the middle, and I just have these 2 intervals, and I also throw out -5 and 9. That's why I have the open brackets, or the parentheses, if you will. And the solution set is whatever set of values causes the statement to be true. That's the solution set. And so there you have it. Any questions on that? Okay. And notice it says type your answer in interval notation, so that's what I'm doing here. And to graph it, I have D as my correct answer. I'm not going to ask you to graph it. Also, I don't think there's a single problem on here where you have to graph anything. These are all like theoretical type questions, just like finding the solution, or finding, asking questions about zeros. What are the zeros? What are the asymptotes? That sort of thing. But I'm not actually going to have you draw anything, so don't worry about that. So here now we have another rational inequality, but it involves a rational function. Okay, so, but you solve it kind of the same way that we did for the last example. You test points in your interval. So this time, you have to determine not only the zeros. So to find the zeros of a rational function, you set the numerator equal to 0. So set numerator equal to 0 to find the 0 of a rational function. So negative x plus 5 equal to 0. If I subtract 5 from both sides, I get negative x equals negative 5. And then that means x equals 5 if I multiply both sides by negative 1. So this is a 0. Then, if I set the denominator equal to 0, I'm going to find the vertical asymptotes. So setting that x minus 7 equal to 0 means that x equals 7. So if I plot these 2 points, 5 and 7, this is a 0. This is a vertical asymptote, but it doesn't really matter. Just note that we have 3 different regions, and this rational function is either positive, negative on each of those 3 regions. So I just picked 1 point to test. So here, if I pick 0 and plug it in, is 5 divided by negative 7 greater than or equal to 0? And that would be false, right? Then between 5 and 7, I'll pick 6. If I plug in 6, I get negative 1 in the numerator and negative 1 in the denominator. And so negative 1 divided by negative 1 is 1. Is 1 greater than or equal to 0? That would be true. And then if I plug in 7, I get negative 2. Not 7, 8. Can't plug in 7 because that would give me 0 in the denominator. Plug in 8, I get negative 3 over 1. Is that greater than or equal to 0? No, that's false. Because negative 3 is not greater than or equal to 0. So now be careful, because we're asking when is it greater than or equal to 0? And if I plug in 5, right? Negative 5 plus 5, I get equal to 0. So 5 is included in the solution set. So we want to include 5. And so we're going to use a square bracket to include 5. However, 7 cannot be included, because if I plug in 7, I'm going to get 0 in the denominator. So I don't want to include 7. So that's going to be an open bracket. So the solution set is 5, including 5 to 7, but not including 7. All right. And there is a problem like this on the test, so make sure you understand this right here, how to do it. Let's see here. Looks like this is the correct one right here. All right, so this takes us to chapter 4. And we have a log expression here. So we have the log, which is the common log because there's no base expressed there, y over 100,000. And it said to expand this logarithmic expression. So to expand, I use the properties of logs. And remember, the log of the quotient, and this is a quotient here because it's a fraction, is the difference of the logs. So this is going to be expanded as log of y minus log of 100,000. And I can write this as 10 to the power of 5. Notice there are 5 zeros. So the exponent on 10 is 5. So this is equal to log of y minus log of 10 to the 5th power. And because this is a power, I can bring it out front. So this becomes log y minus 5 log 10. And remember now, this is the common log. So when there's no base written here for the log, it's understood to be 10. So think of this as log base 10 to the 10th. And to calculate this, just ask yourself, what exponent on 10 equals 10? Well, that would be 1, right? So this, since logs are exponents, this is equal to 1. So this becomes log of y minus 5. And you'll notice in the instructions that it says, where possible, evaluate logarithmic expressions without using a calculator. And that's exactly what I did. Of course, you'll have your calculator, so you don't need a calculator, but if you want to use it, I'm not going to say you can't use it, but I did it without a calculator, so there it is. Same problem here. We have log 5 of 625 over y. And let me think. How many powers? I think that would be to the 4th power. So 5 to the 4th power, I think, is 625. I'm not sure, but we'll find out. So since logs are exponents, wait a minute, let me think. 5 times 5 is 25. Times 5 is 125. Yeah, that would be right. So it's 4 is the exponent. Just remember, logs are exponents. The base is 5. 5 to the 4th power is 625. Notice I'm using the difference because this is a quotient, right? If it were multiplied, I would use a plus sign. As here they're multiplied. So because this is an exponent, this is going to come out front in front of the log of z. So this is going to be 2 log z, right? The z squared, this is the exponent, comes out front, and I have log z. And now because they're multiplied, it's going to be plus log y. So I'm expanding. And I can't simplify this at all. I forgot the bases in there. I should put the base, it's base b. So don't want to forget the bases. Log base b. We don't have to know the base to expand it. Okay, this is a difference. See the difference here? Now we're doing the opposite. We're condensing. So we see the difference. A difference becomes a quotient of a single log. So this is going to be log. And then I've got a quotient. The numerator is the positive one, 3x plus 2, and the negative is in front of the one with the denominator, so that's going to be x. And it's a common log, so I don't need a base there. Again, we're condensing. So this is going to become, so now because this is plus, it's going to be a product. And because of this constant in front, that's going to be an exponent on z. So we have log of y multiplied by z to the power of 14. So I'm condensing now. So I think there are two problems on there where you're condensing and two where you're expanding. And let's see what we got here. Notice that here we have an exponent. It's a fraction. This means that it's taking the 6th root of y, and then we're multiplying that by z. So it's going to be the natural log of the 6th root of y, and then multiplied by z. Now, I'm not sure if that z, if I need parentheses around that or not. No, I don't. Okay. I'm kind of zipping through this really fast. Oh, change of base formula. Make sure you know how to use it. There's at least one problem where you have to use the change of base formula. So let me show it what it is. If you want to calculate a log, so log base b of a equals the log of a divided by the log of b. Remember, the base is on the bottom. So you just take these two numbers, and your calculator has the common log in it, or you can use the natural log. In fact, you can use any log, but these are the two in your calculator. So you just take log base b of a. You don't have base b in your calculator, so you use the common log, and you go log of a divided by log of b, or you take the natural log of a over the natural log of b. This is the change of base formula. There's at least one question on the test where you have to use this formula. So just remember, the base is on the bottom. You take the natural log of each. So here we have this log base 0.6 of 17. Is going to be the log of 17 over the log of 0.6. Okay. And that takes us to the end of the class period. So I'm going to let you calculate that because you probably have some different answer there. But just take on your calculator, take the log of 17, then close the parentheses, and then divide by the log of 0.6. You have to use either the common log or use the natural log, but you can't crisscross them. You have to use just the common log for both numerator and denominator, and just the natural log for numerator and denominator, but you get the same answer both ways. So, all right, so I will pick up for my next period. We only have 3 questions more, but I will start off with chapter 4, and then I'll post a video from that period so that you have both. And if you make sure you use that list as your guide, and I will update that list as necessary. Oh, there are lots of questions, not a lot, but I would say 6, probably each worth about 3 points, where you have to change from exponential form to logarithmic form. So make sure you know how to do those. Do the review. It's real important. Do the review. Okay. Have a good one.